This video is going to look at op-amp stability, in particular driving a capacitive load and how to prevent oscillations. So first we're going to look at the non-inverting op-amp. On the bench I have a TL083 as an example, and later we're going to investigate driving the capacitive load with it. And to do that we're going to look at bode plot analysis, loop gain, step response, and eventually try to fix our problem with lead compensation and with MATLAB along the way, checking our work. So here is what I have on the bench. I'm feeding about a 70 millivolt peak-to-peak square wave into my op-amp here. And I have some variable gain set up with a potentiometer here. And the maximum gain is about 100 or 40 dB, and the minimum is just about 3 dB. And I'm gonna see how the scope traces look as we vary the gain, but with the capacitive feedback as well. So here's the minimum gain here and the maximum gain of 100. So to get the open loop gain of an op-amp, I have the data sheet here. And in figure 8, we see that there's a DC gain of about 200 volts per millivolt. It's about 100 and something dB. And to look at the pole locations, it's handy to look at the points where the phase shift is accumulated about 45 degrees. And you know that a single pole can only accumulate 90 degrees of phase shift. So this looks like about 30 hertz for the first pole and maybe about 7 megahertz. Doesn't have to be perfect. But if we just plot those in MATLAB to look at our step response and bode plot, we see something like this. And we don't really see much overshoot on the scope, but it might just mean we have some extra damping in our circuit and whatnot. Again, this is just to kind of check our work. Here we see we have our loop gain plotted, which is the blue curve, and our actual transfer function with unity gain. And we know from stability that the loop gain is A times beta, and that's what determines stability. And here we have it on some graph paper as well. And the loop gain is really the difference between the curves of A and 1/beta by log rules in the top right. And we see that for unity gain, here 1/beta is just 1, and our loop gain is really big for a large bandwidth of frequencies. But if our beta is such that our loop gain is smaller, where we have our 40 dB voltage gain set up on the op-amp, then we cross 0 dB for the loop gain earlier, which means that our stability is greater for smaller loop gains, but our error increases. So yeah, we see here the closed loop gain is only approximately 1/beta for A beta is much greater than 1. And here's our phase as well. See about a phase margin of 60 degrees, which is what the MATLAB script is showing. So then you might be asking, why do we make A beta big at all if we know we lose stability? And that's because our closed loop gain, if we want to control our 40 dB or whatever voltage gain for our op-amp configuration, we know that if the closed loop gain is the difference between these curves, assuming this is unity gain, then we're following this curve. And if beta is if 1/beta is larger, so we have our voltage gain of 100, we'll follow this 40 dB curve, but we'll start to lose accuracy once we get into higher frequencies. So if we look at here, 40 dB curve, this is our closed loop gain until we get to about a 50 kilohertz or so, and then we start to lose accuracy. And how did I find the loop gain to actually put it in the MATLAB? Well, for the non-inverting configuration with no load, it's actually pretty easy, but in general, you want to solve for the loop gain by breaking the feedback loop here and calculating V-return over V-test, where V-return is voltage fed into the inverting terminal, and V-test is the voltage that's amplified by the op-amp's intrinsic gain here. And if we do that, we can follow some equations and end up with this as our loop gain. And as I said before, there's a trade-off. If AB is high, lower stability, but lower error as well, which is good. And if AB is low, then we have higher stability, but higher error. And now let's look at driving the capacitive load. This is where things get more interesting. If we solved before for V-return over V-test, where here we're saying that the error voltage between the plus and minus terminals is V-test, we can do some algebra and pause it if you want to look at this. But the final result is this, and we see that we have our closed loop gain we want, so 100 or 1 or whatever this is our determined by our resistors, our op-amp transfer function, open loop, and everything here is just what we had before. But adding that capacitor, we see we add an extra pole to our loop gain, and that extra pole will affect our stability. So if we look at what that looks like on a bode plot, we see with our capacitive load is I put a 224 nanofarad cat, and it's assuming our output resistance is 10 ohms of our op-amp. We see that we have this added pole here, and we have another minus 20 dB per decade breakpoint at that pole, and that pole also accumulates 90 degrees of phase shift. So now by the time our gain gets to 0 dB, we have much more phase shift accumulated, and it's less stable because we have less phase margin. So let's see what that looks like here. If I add this capacitor into the circuit, we see we get a ton of oscillations. So let me zoom out here. And if this is at maximum gain of 140 dB, and if I lower the gain, we see the ringing is more pronounced. It takes up more of the waveform here. And that's why unity gain is hardest to compensate for, because at the smaller 1/beta, remember that means our smaller 1/beta, that means our loop gain is higher, and it means we have more time to get to that 0 dB point, which means we have more time to accumulate phase shift and give us negative phase margin. And let's lower the frequency a little bit so we can see these oscillations more. And use a relationship of percent overshoot and phase margin to kind of see how much phase margin we have in real life, and then we'll compare with MATLAB as well. So if we crank our gain all the way back up, you see maybe that's about a 50% overshoot or so of the final value. And if we take this curve, look at percent overshoot, 50% means we have a damping ratio of about 0.2. At a damping ratio of 0.2, we have about 20 degrees of phase margin. So let's look at that here on the MATLAB. And yeah, 19 degrees of phase margin for our gain of 100. That's this guy right here. And here's all the bode plots. They all have the same phase shift, of course, because it's just differing voltage gain from the resistor configuration. And now let's lower the gain all the way down to just 2-ish. And we see that overshoot is almost 100% of the final value. If we look at this graph here, percent overshoot, we see that damping ratio for a percent overshoot up here. It's really low. We might have 5 or 10 degrees of phase margin. And that's what MATLAB is showing as well. Look at that. So how do we fix this oscillation coming from driving this capacitive load? Well, we can do one way is lead compensation, which is adding a capacitor in the feedback path. And before I get to that, let's say, why don't we just lower the loop gain A beta? Well, if we want our gain of say 1 in our voltage follower, lowering A beta means that if we just change the resistor values to lower beta, then let's say here's a lower A beta, we'll cross over 0 dBs earlier, have a better phase margin, but now our DC gain is 100. And if we want to still have a gain of 1, we need to do something else. So if we can have a way to add a 0 somewhere in A beta in the loop gain, then we'll gain 90 degrees of phase shift in the opposite direction. So rather than losing 90 degrees, we'll gain 90 degrees of phase shift. And then hopefully by that time, our gain has dropped down to 0 dBs, and then we don't really care what happens afterwards with the phase. So the basic idea is we want to delay our net 180 degree phase shift until our current roll-off hits the 0 dB point. And so we need a 0 to happen before any later poles occur. And in fact, here I've just done the math to look at what lead compensation looks like. So here's our compensating capacitor, C sub C. And if you want to follow this, you can. But it turns out our loop gain A beta, which I've just defined as V return over the V test, as in the previous example. We have our open loop op-amp transfer function, which, as we had before, with our resistor configuration. So this is still our DC gain. We have our pole from the load we're driving, this guy. And now we have an extra pole and an extra 0 from our capacitor in the feedback path. And we know that our 0 frequency is always lower than the pole frequency, which is what we wanted, because R2 is always greater than R1 in parallel with R2. And as a rule of thumb, usually you locate the 0 at the old crossover frequency of your transfer function where you'd like to add phase shift to. So here, for example, is our gain of 10 on the scope. Here's without the capacitor and with the capacitor. And how I chose that value is I looked at the 0 dB crossing point of the loop gain without the compensation capacitor. And we see here, the red curve is that, and we hardly have any phase margin. But if we place the capacitor such that 1 over C sub C R2 is the same frequency as the old crossover frequency, so in this case, 7 times 10 to the 5th radians per second, or up thereabouts, we could see that we actually start adding phase shift before other poles kick in and we lose that phase shift. But that gives us enough margin by the time we hit 0 dB that we have, in this case, 50 degrees of phase margin. And that checks out with this. That looks like 50 degrees of phase margin. And so we can go and look at, here's a gain of 2. So I just have I have a 100 ohm resistor, feedback is R2, and 100 ohm from the inverter terminal to ground is R1. And we see this is the hardest to compensate. Voltage buffers and low gain are hardest to compensate, but we still, if we locate this new capacitor down so that our 0 is over the old pole, we have a little bit extra phase shift. So in that case, I have this capacitor here, which turns out to be proper. So now if a gain of 10 happens, we see we're attenuating too much and we actually have trouble reaching that slope. So here's increasing the gain, and the big capacitor relative to the gain is making us really slow down a little bit. So let me get to channel 1 and move it down, and we see here's with the compensation capacitor versus without. Absolutely way better. And if we go to the extreme, let's get our gain of 100 up. This is a gain of 100 with that capacitor that was sized for the gain of 2. We see that that capacitor is way too big, and even though it's working, it's damping our oscillations too much. And here's a smaller capacitor I've sized properly. And we can see, look at that, it is damping just enough, but not too much where we're rolling off our final value. And I'll show you the gain of 100 in MATLAB as well. Here's our old crossover frequency. I've located C is 1 over the R2 value times the crossover frequency of the uncompensated. And that's how I've solved for C for all these. And look at this extra phase shift we get from that. And just to look in the time domain, we can confirm what we're seeing. Here, obviously the higher curve is the higher gain. This is uncompensated. So here, this would be uncompensated. Versus compensated. Uncompensated versus compensated. Still a little bit of overshoot, and we see there's a trade-off between you're removing oscillations, but now your rise time is slower and stuff like that. But your overshoot's much better, much lower, and your damping's higher.